This is problem 629, it's on page 279. If the maximum force that any member can support is 4 kilonewtons in tension and 3 kilonewtons in compression, determine the maximum force P that can be applied at joint B. Take dimension D to be 1 meter. So they've given us a figure that defines the structure, but everything is related symbolically. Often students have a lot of trouble with symbolic problems without numbers. I don't think it's really a problem per se due to the fact the problem or the question has no numbers. I think it's a problem of understanding. And understanding a problem like this that has no numbers helps quite a lot when you work a problem that has numbers, because it's the underlying mathematical relationships that make a difference that you really need. So distance D is here and here, as well as here, D over 2 here, and the whole thing's symmetrical, except the load, of course, is not symmetrical. We've got some point names, E, or joint names, D, F, A, B, and C. And we'll begin with the free body diagram and maybe a little bit of geometry. Let's make another sketch of the entire body. EY, EX are applied at point E. Reaction AY at point A, and then force P applied to the left at the top. Now, to deal with the geometry, what I decided to do was to draw point, let's see, what would this be, BC. We know that the height of point BC is 1D. And the length, let's see, how can I do this? So the triangle I'm playing with is right there. The height of that triangle is 1D. What about the base length? Well, the base length is D plus half of D. So this must be, put B up here. This length must be 1.5D, or 3/2 D. So what size is the hypotenuse? Well, we take 1 squared plus 1.5 squared and then the square root. And that would give us the hypotenuse. If you take 1.5 squared, you get what? 1.5 plus 0.75, so 2.25. So 2.25 plus 1 squared would give us 3.25 squared. Take the square root. So this side is root 3.25 times D. Notice all three sides are just scaled by distance D. On the other hand, if we consider this triangle, let's erase the other one, we don't need it anymore. So the triangle that deals with points D and E, well, what do we know? Well, let's see, we know that the base of this triangle is 0.5 D, or half of D. And we know that the height is just 1D. So could we figure out the dimensions here? Sure, 0.5 squared plus 1 squared, so 1.25 of D. So there's the geometry we need. I'm going to make a note of that geometry over here, because I'll probably need the space and I'll end up erasing that. So that's part of this triangle. Let's be careful. And this hypotenuse is root 1.25D. All the other dimensions we need should be there. So I think we're done with the geometry. Now with the free body diagram, let's sum moments, if I can write it in, about point E taking counterclockwise as positive. So we're going to put our pivot point right here. And notice that the moment of P and the moment of AY must cancel one another for static equilibrium. So P times what? Well, its moment arm is a height of 2D. And of course, P causes a positive moment about E, whereas A causes a negative moment, or at least AY causes a negative moment. 3/2 D is its moment arm, or, 1.5 D. But from the center line over to A is the moment arm of AY about E. Anyway, the sum has to come out to 0. So now we can write AY in terms of P. Notice the D cancels. And so we would simply get AY equals, well, simply 4/3 of P. So I'm going to draw the reactions in blue and just write them AY equals 4/3 of P directly on the diagram. Now, if we sum forces in the vertical direction, we get that EY is minus AY equals 0. Oh, I'm sorry, plus AY equals 0, excuse me. So what this tells us is that EY is the negative of AY. So if we were to draw EY in our usual positive direction, we would get negative 4/3 of P. Let's put a coordinate system on this so you know what we're doing. Okay. Now what about summing forces in the horizontal direction? Well, summing forces in the horizontal direction says that EX must be equal to P. Let's make a note of that on our diagram. There we go. So now we've got all of the reactions and geometry for future use. Okay. So negative 4/3 P. In other words, point E is actually pulling down, while point A is pushing up, and so forth. Now, we're supposed to use the method of joint, so let's do that. Let's begin with point A, because if we begin with point A, we know the magnitude of the load here, 4/3 P, and we should be able to figure out AB and AF. So I think what we'll do is make a table of all the loads so we can keep ourselves organized. AB, AF, these two BF, not sure what order I'll solve them in, it doesn't matter, BD, just jotting them all down, FE, ED, and then DC and BC. Okay, so the force in each of these, and whether it's tension or compression, will be important. So alignment line so I can keep all this straight. And there we go. So back to point A. Point A has load AB, and remember AB, load AF, and the reaction AY. So if we sum forces in the Y direction, that will be beneficial because only AB will appear in that equation, since AF has no vertical component. So AY plus AB in the Y direction should come out to 0. So AB in the Y direction should be the negative of AY, but AB in the Y direction, well, let's see. This is AB. Its vertical component is D over root 3.25D. That's what we need to, that's our factor to multiply by in order to get the Y component. Now obviously the two D's cancel, and what we'll end up with is AB is, well, negative root 3.25 of AY, but AY, well, you know what, I'm doing that too fast. Let me slow down. AB is negative root 3.25 AY, but AY is, well, let's see, 4/3 P. Now the root of 3.25 doesn't come out nicely, so I'm just going to leave it that way. Anyway, so that tells us that AB is compression, root 3.25 4/3 P. Now if we sum forces in the horizontal direction, that should yield AF. In fact, we'd have AF plus ABX, and no AY, of course, equals 0. And so AF will just be the horizontal, well, the negative of the horizontal component of AB. Now, AB, what do we need to multiply AB by in order to get the horizontal component? Well, let's see. That would be this length, which is 1.5 of D, over the hypotenuse 3.25, or root 3.25 D. So what did I say? 1.5 of D over root 3.25 of D. The D's cancel. And now we can plug in AB. Now AB is itself a negative thing. Remember, it is compressive. So, and again, I've drawn a tensile as usual. So I need to make this negative root 3.25. Notice this comes from here, 4/3 P. That takes care of the AB part, times 1.5 over root 3.25. That comes from the second part. So the 3.25's cancel, the negative signs cancel, and we just get 4 times 1.5 over 3p. Now that's something we can make sense of because, of course, 1.5 is 3 over 2, so we get, 4 over 2p, so in other words, 2p. So the magnitude of AF must simply be 2p. It's positive, so it's a tensile load. Okay? And that's all we can learn from point A. Where should we move next? Well, we know F, we know AB. If we go to B, we're going to have 1, 2, 3 unknowns in the equation. That does not look promising. How about at F? If we move to F, well, that also doesn't look very promising, does it? Okay, so could we start somewhere else? Sure, what about E? If we start at E, we know the reactions, and that would yield F, E, and ED, which then would allow us to move up to F and then maybe to B from there. So let's take that approach. Let's start at point E, or continue, I should say, at point E. We know there is EY, EX, FE, and DE. Now I've drawn these at too large an angle. Forgive my drawing, they shouldn't have near so much angle, but it's just a schematic anyway. If we sum forces in the Y direction, we'll get the vertical component of FE and the vertical component of DE. EX won't appear, but we'll also have plus EY, and that sum then comes to 0. Now, one thing about this you should notice. Well, I'll say that in a minute. We'll prove it from the sum of forces in the horizontal direction. So if we want the Y component of FE and DE, it'll be the same factor. So let me do this. Let me say FE plus DE, and I want the Y component of those two. So again, it's the same factor. What would it be? Well, it's the height D over the hypotenuse. So D over root 1.25 times D, and there we go. So that's the Y component of FE and DE added together. And that would then be equal to negative EY. Now notice EY itself is a negative thing, so really the right-hand side of that equation is positive, but let's cancel in the D, by the way. Okay, what about, but notice this is one equation and two unknowns. Could we sum forces in the horizontal direction and see what happens? Well, there we have FE's horizontal component pulling against DE's horizontal component. And there's also EX applied at this point, or at this joint. So the sum comes out to 0 for static equilibrium, and so we'll rearrange just a bit, noticing that the factor again for the X components of FE and DE are the same. We can write negative FE plus DE multiplied by D over 2 over root 1.25D. So D over 2 over root 1.25D. Cancel the two D's. And let's not forget, we still have this term, right? All I've done is take care of these first two. So EX, well, I was going to put it on the other side. I guess I'll do that. So negative EX equals, and EX is simply P, so equals negative P. Okay? Now, let me erase the intermediate balance equations. And now notice, if I take these two equations and simply sum them, the two FE's will cancel, but the DE's will add. So I'll have 2 DE. Actually, no, not quite. No, the two FE's do not cancel. I know what I forgot to do. I need to rearrange this just a little bit. Let's put the root 1.25 on the other side. So multiplying through by root 1.25. There we go. And this one as well, but of course we've got an extra 2 here. So let's see, let's just do this. There's a negative P, so equals 2 root 1.25 P, but it should be a negative thing. There we go. Just a little bit of algebra there. Now we can add them a lot easier. Okay, so now if we add, now the FE's cancel. And we'll have 2DE on the left-hand side. And on the right-hand side, oh, you know I never plugged in the EY. What is EY? EY is negative 4/3 P. So the two negative signs cancel. Now let's try one more time to add them. Okay, so 2DE, and notice both have the same factor of root 1.25, so let's pull that out. The first one will be 4, well, they have a P there as well, so let's pull that out too. Taking care of the P and the root 1.25 in both terms. But then we'd have 4/3 minus 2. Okay. Now, we can simplify this a fair bit. I guess the easiest way to see it is to say that 2 is the same thing as 6/3. Right? So if we take 6 from 4, we get negative 2/3, which, oh, yeah. So this becomes negative 2/3. That makes sense. And then this 2 will cancel with that 2. Okay. So now what we've done is solved for DE. That was a little bit of work. ED and DE are the same thing. It doesn't matter what you call it, it's this member here. So we'll put it right here. And notice it's a negative thing. So this is a compressive load and has magnitude, what's the best way to write this? I guess root 1.25 P over 3 so that it fits on the line. And it's negative because it's compressive. I just put that over in the other column. All right. However, now that we've done that, now that we know the magnitude of DE, notice I canceled these because I added the 2. Now what I could do is simply plug in the known value of DE to solve for FE. So FE would be equal to root 1.25 times 4/3 P minus DE. All right, so let's see what we get. Root 1.25 4/3 P minus DE is compressive. So that would be negative root 1.25 P over 3. So we're actually adding. So basically we need to add 4/3 with another 1/3, so to speak, right? So 4/3 and 1/3, that's 5/3. So this would be 5/3 root 1.25 P. And so that would go on FE. Now notice it's positive, so this is a tensile load. So 5, let's see, how do I want to do this? How about 5P root 1.25 divided by 3? Okay, so let's put a check mark by the various joints that we have solved so we can kind of keep track of it. We used A already. We've just used E. And I think that's it so far. Okay, where should we go next? Well, thinking about F, now we know the load AF, we know the load FE, and so there are only two unknowns, BF and DF. So let's go there next. Let's go to joint F and see what we can find. Now joint F has FB, FE, FD, and AF. And let's see, if we sum forces in the horizontal direction, we get negative AF plus FD plus FBX plus FEX equals 0. So maybe I shouldn't have begun with that one. How about if we begin with the sum of forces in the y direction? Because notice I've got two unknowns in this equation. We begin with the y direction. We should find out something about the relationship between FE and FB, because notice AF and FD will not appear. As a matter of fact, what we'll find is that the y components of the two are equal and opposite. So FBY, let's try F not E, FBY equals FEY. But of course, notice that the geometry is symmetrical, right? The angles and the dimensions and everything are the same. So if we took the y component here, the factor would simply cancel. So FB is equal to FE. So whatever the magnitude is, those two are the same. So what that means is the horizontal components will also be exactly the same. Okay, the only purpose of the y component equation, as far as we're concerned, is to show that FB and FE are equal to one another. So let's continue with that approach. FB plus FE, and I'm putting parentheses around them because, again, the horizontal factor, or the factor to get the horizontal component of these two, will be exactly the same. It will simply be d over 2 over the length of the hypotenuse, which is root 1.25 d. So d over 2 over root 1.25 d. And that gives us the x component. So I'm going to leave these on this side and move the other terms to the other side. So AF minus FD. And of course these two are equal, so I can simply say, well, this is just 2FE, for example. So those two cancel, the d's cancel, and what we can say then is that FE is equal to root 1.25 times AF minus FD. Okay. And I went a different way when I saw this before, so let's just continue at the board. So root 1.25, AF is 2p, it's in tension. FD, oh, is it FE that we know? Huh, we know FE. I solved for the wrong thing. Let me try that again. Yeah, let me go from here. So I should have, I already know FE. I should have solved, let's see, for what? FD, right? Or DF. Do I not have it over here? DF. 1, 2, 3, 4, well, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. Yep, I missed one. What I missed was apparently FD. We'll squeeze it in at the bottom and see if that works. So now I've got all 9 members. So FD is what I want. So FD would be equal to, let's see, AF, just pulling this to the other side, then take this term to the other side, minus FE over root 1.25. There. And so AF is 2p in tension, FE is 5p over 3 root 1.25, its intension. Now the negative sign just comes from the equation. I assumed FD, or FE, I assumed it was in the positive direction. Okay. All right, so, I just plugged in FE. I forgot to divide by root 1.25. There we go. Yeah, so FE is right there, and I've just copied it over. So these two do in fact cancel. And 2p is the same thing as 6/3 p minus 5/3 p. So 6 minus 5 is 1, so this is p over 3. So FD is simply p over 3, and it's positive, so it is a tensile load. All right, so we're making progress. That's everything we can do for point F. And now we've solved, I guess I should be checking these off. Point F. Where could we go now? Well, remember my strategy was to walk through this system as far as I could. And so we could go to B if we wanted to, because we know these two. There would only be two unknowns. Why don't we go to D instead? Because now notice we know the load in FD. So again, there's only two unknowns there. So that's just what I chose to do. But you could just as well go to B. It doesn't matter. I think I left B for the end for a verify, a check. So let's see, we have BD, DE, we would have FD, and DC. Okay, so those are the forces and the members about D. So if we sum forces in the vertical direction, we get BDY's component minus DEY's component, and I think that's it. And so what we'd find from this is that BDY equals DEY. Now where is BD? It's right here, and DE, it's right here. Again, these two are geometrically symmetrical. And so the factor y would be simply d over root 1.25d. It's the same factor for both. So what this means is that BD and DE are also equal to each other, but we already know one of them. In fact, we know DE or ED. And so the other one, BD, is the same. So BD is the same as ED, it's root 1.25p over 3. And should be the same, it should be compression. Okay. All right, so what else could we do? Well, we could sum forces in the horizontal direction. It would be negative FD plus DC minus BDX minus DEX equals 0. Okay. All right. So from here we could say, well, negative FD plus DC minus, but be careful. Remember, these two are the same, right? BD and DE were the same, and so we can simply write 2 BDX equals 0. Okay, so let's plug in and see what we've got. Well, what is FB? FB, oh, we don't know FB, we're trying to find it. Wait a second. Oh, I'm copying things down wrong, that's the problem. I went from FD to FB, I have no idea why. That should be FD. So hopefully we know FD. Yeah, here it is. We know FD, so negative P over 3, the negative sign comes from the equation, P over 3 comes from here. It's tensile, so positive, plug in. So I said the negative comes from the equation. DC, not known, let's just leave it as DC. Minus 2 BD. Well, BD, we need the horizontal piece, but what is BD itself? Well, it's root 1.25 P over 3, so let's put that in. But we want the x component. I guess I don't need that. So multiply by what in order to get the x component? Well, that would be d over 2 divided by the hypotenuse. So d over 2 divided by root 1.25d. Again, the two d's cancel. The 1.25's cancel nicely. And this sum comes out to 0. I don't know why I didn't solve for dc here, but let's go ahead and do that. dc equals, pull this to the other side, p over 3. And then minus here will be, oh, the 2's will cancel. The minus will become plus because we're pulling it to the other side. So plus p over 3. And yeah, it looks like everything else is canceled. So this is simply 2/3 of p. And it's positive, so it's tensile. So dc is 2p over 3 tensile. No, I made a mistake. How did I make a mistake? Let's see, I did something wrong here. Negative FD makes sense, DC, yeah, that'll make sense. BD. I neglected to note that this was compression, so I should have plugged in negative here, so the two negatives cancel, and when I pull it to the other side, then it'll be negative, so then we would get 0. There we go. So DC comes out to not 2/3 p, but 0, and so tensile or compressive doesn't make any sense. There we go. And that makes sense if you think about it, because if you look at point C as a free body diagram, there's only two things going on there, right? And so there's no way, we could have solved C from the very beginning. There can't be any load in either member BC or DC, because there's no way for these two forces to come to static equilibrium on that point. And so, considering point C, it's pretty obvious that BC is also 0. So we really didn't even need rows for those. We could, and that should make some sense, right? If you remove these two elements, or these two links, we don't need them, do we? They're just hanging out there, okay? So there's no load in those two links. So what does that leave? We don't have BF. No, we do. Well, but we do have F. I thought we got BF along the way. Let's see, I must have missed something. Yes. Yeah, I didn't write this down. I skipped in my notes. When I had point F, way back then, I was looking at point F, and I noted that FB and FE are equal to one another because of summing forces in the vertical direction. I neglected to write down that they were the same. I neglected to fill it in the table. So BF I didn't fill in, but I did fill in FE. So I should have put 5P root 1.25 divided by 3 here, and then noted that it would be the same as FE in terms of tension or compression. So there we go. All right, so now our table is completely filled in. There we go. And what I did is I left point B as a check. Let's see, I think we've already gone through point D. Yes, that's the one we just worked in point C. So now let's check and see if point B is in fact in static equilibrium. So let's see, AB. No, I don't like that. Let me try again. FB, BD, and over here BC. Now we know that BC is 0, so let's just pull that. Well, let's just do it this way. So that way I don't have to add it into the equations. But now let's sum forces in, let's see, I started off with summing forces in the horizontal direction. We'll have negative P, so that takes care of that piece, minus ABX minus FBX plus BDX, and that's it. Now we know what each of these should be, so let's just plug them in. So negative P is The first term minus ABX. Well, AB is root 3.25 4/3 P, but we need the horizontal component of AB, and that horizontal component would be, well, let's see, what, 3/2 D over the hypotenuse, so root 3.25 D. The D's cancel, 3.25's cancel, and the 3's cancel. Okay? And so far we've taken care of those terms. So minus FBX. Well, FB, we know what it is. Same thing as BF, 5/3 P root 1.25. I need to be careful here, though. I'm not being careful about tension and compression. Let's see. Let's check AB. AB is in compression. So if I need the negative of AB, I should have plugged in negative of negative is positive, okay? Because AB is in compression. Let's be careful. What about FB? Let's check the sign. FB is tension, so plugging it in according to the sign in the equation is fine. I don't have to flip the sign. But it was 5/3 P root 1.25, but I only want the horizontal component of it. So for FB, FB is right here. The horizontal component would be D over 2 over, well, over root 1.25 D. Let's just write it down. So D over 2 over root 1.25 D. Make sure I haven't made a mistake. Yeah. And the 1.25 cancels. That's nice. Okay, so that takes care of this term. I'm out of space on the video, so I'm going to move to the next line and add BD. Oh, double check. I think I checked the sign. Yeah, it's tension for the last term. So BD. BD is compression, so I'll need a negative of BD, root 1.25. BD P over 3. But again, I only want the horizontal component. So let's multiply it by whatever factor necessary to get the horizontal component of BD. So that's D over 2 over the hypotenuse. D over 2, and this hypotenuse is root 1.25 D. So again, the 1.25 square root and the D's cancel. And the question is, does all this come out to 0, or did I make another mistake along the way? It should come out to 0. Let's see, notice that the P would cancel throughout. 2, 3, 4 of them. And so what we'd be left with is a negative, let's see, well, nothing. Because that doesn't count. We're left with a 1 here. Sorry. So it doesn't just go away. So negative 1 from there, plus, all that's gone. We've got a 4 over 2, which is just 2. It's the only thing left. It's like a big battle where there's a lot of carnage. But anyway, everything's gone except for 5 over 6, because 2 3's are 6. And then for the last term, we've got minus 1/6, because 1 over 6, 2 times 3 is 6. So let's see if this works. Let's see. 1 minus, well, 5/6, well, that would be minus 6/6. So, yeah, that works. 1 minus 1 is 1, or is 0. So everything works. So what we've done is we've verified that all of these loads are correct, but that's not the question. The question is, what's the maximum load P that we could apply, given that we have a maximum, and I don't think I wrote this down, but we have a maximum of 4 kilonewtons in tension, 3 kilonewtons in compression. So either negative 3 kilonewtons or positive 4 kilonewtons are the maximum load, so compressive load, tensile load. So where do we see the worst case scenario? Well, let's see. If you look at the various, let's see, let's highlight in red the various compressive loads and compare them. There are only 3. Root 1.25 P over 3, that's the same as BD. So don't have to worry about that. We just need to compare here. And 4/3 P root 1.25 would be worse than root 1.25 P over 3 for sure. So we're not worried about this one either. That's the concern for compression. What about for tension? Now there we got what, 1, 2, 3, 4 to compare. 2P is definitely bigger than P over 3, so we're not worried about that. None of these matter, these are zeros. And these two are the same, FE and BF. But which is bigger, 2P or 5/3 times root 1.25? Well, you need a calculator to calculate the square root of 1.25, but it turns out that 2P is the one to be concerned with, because 2 is larger than 5/3 times the root of 1.25. And I guess you can't really see that. You'd have to know that 5 times root 1.25 comes out to less than 6. But anyway, so for the tensile load, the worst case scenario is 2P. I should have marked that off just as I did the others. But for the compressive load, the worst case scenario is root 3.25 4/3 P. And so what we can do from these is solve for P. And let's not forget, this is a compressive load. I should have put a negative sign on there. Okay. So solving for P, we'd have 3 times 3/4, invert and multiply, 1 over root 3.25. And these would all be kilonewtons, of course. So if you go through and do the math, this comes out to P equals 1.248 kilonewtons. That 1.248 kilonewtons will cause a compressive load of negative 3 kilonewtons, and that load will occur in AB. Let's see, yeah, that's the only place that occurs. What about the tensile load? Well, that's pretty easy. P equals 2 kilonewtons, right? Just divide both sides by 2. So if P is 2 kilonewtons, it's going to be above this, and we'll already have far exceeded, or we will have exceeded the compressive rating in member AB. So that's what limits. So it's member AB in compression that limits, but what member limits in tension is AF, right here. But of course, AF won't reach the 4 kilonewton maximum tensile load before AB reaches the maximum compressive load due to load P going up above 1.248 kilonewtons.